Hello, everyone. I think we're live here, so very welcome to our webinar, Maximising 3D Printed Implant Performance with the Material Science Perspective. So I'm Dr. Shane Keaveney. I'm the R&D Manager here at Croom Medical, and I'm joined by my colleague, Dr. Bryan Naab. So we're going to talk a little bit about the material science perspective in terms of maximising 3D printed implant performance. And our motivation around this is just driven from our knowledge and our experience within additive and also material science and development of materials and parameters. So we thought it'd be good here to take the opportunity to share some of our knowledge and open the floor for questions later. So as I said, I'm the R&D manager here at Croom Medical. I've been with Croom since about 2019. Worked originally as an R&D engineer and then the R&D manager. And I'm very focused on trying to build our portfolio of research projects, as well as our internal development projects within our MPI. So I'm going to talk to you a bit about what we do here at Croom, a bit about our additive manufacturing services as well. And then I'm going to hand it over to my colleague, Dr. Bryan Naab, who's going to talk you through material characterization methods, so material test methods and characterization methods, and metal fatigue, so fatigue of metals and what influences that, as well as how to maximize the 3D printed implant performance with respect to these. So just looking at Croom Medical and who we are. So we are a manufacturing partner for orthopedic implants. So our core focus is the manufacturing of implants, orthopedic implants. So looking at total joint replacement, spine, foot and ankle, trauma and extremities. And we're focused on being able to create these devices through a number of different methods. So whether it be additive or subtractive, but also we have a very core focus on the finishing. So on the polishing, on the finishing, whether it be a cast part, a machined part, or an additive part, and doing that at a high volume scale. So we've been in business for over 40 years. We were set up in 1984. And we're a 24/7 facility here with over 170 plus people. And we have our ISO 13485, 14001. And of course, we are FDA registered as well. And you can see a little bit on the video that's playing here in the background, just about some of the types of machines, operations, processes we do, from grinding, machining, 5-axis machining, sliding head type turning, all the way to our inspection, CMM type systems, and our material test lab, which has been shown here for some tantalum. And here we'll see some tensile testing within our own materials lab as well. Now, part of our materials lab is really coupled with our additive manufacturing suite, where we're able to look at, okay, what's happening with their process, how is that influencing mechanical properties, which Bryan's going to talk to you a good bit more later. So just to look in terms of what do I mean by those processes I mentioned, here's just a nice list in terms of our 5-axis grinding, CNC machining, turning, mill turn, turn mill, as well as robotic polishing systems, EDM, the list goes on. And of course, our additive systems as well, which I've listed here. So for additive, we really see ourselves as a one-stop shop into serving the world's leading orthopedic innovators. So we're here to help you along on your journey, from whether it be a prototype system or a product that's already in the market that you need more capacity, or whether you want to explore new materials such as tantalum or whatever it might be, or new alloys. So we do have several systems, and mainly we focus on SLM systems here. And we work with titanium, tantalum, cobalt, chrome, these types of things. And as I said, we can help at several different points of your journey. So whether it be serial production, or whether it be doing design for additive manufacturing, development of new processes, whatever it might be, all the way through to taking prototypes into serial production. So with that, I'm going to hand it over to Dr. Bryan Naab for the main part of our presentation, our webinar, and he'll introduce himself now. And I'll come back to you later. If you do have any questions, you'll see a Q&A box here on the screen. So feel free to drop questions in as we go, and we'll come back to that at the end then.
Okay. Thank you very much, Shane, for that introduction and overview of Croom Medical. My name is Bryan Naab. I'm a research engineer here at Croom Medical. I previously did a PhD in materials science and engineering, specifically focusing on fatigue prediction in additively manufactured Ti-6-4. Here at Croom Medical, I support the R&D team with materials testing and other research projects, such as commercialization of new alloys for additive and development of medical devices leveraging additive manufacturing. So I will start with a brief introduction on the topic. So I will focus on additive manufacturing, advanced characterization methods, and AM microstructures and defects. So what I really want everyone to take away from this talk today is how the processing, specifically additive manufacture processing, as well as post-processing, can influence material properties such as the microstructure and the defect content of additive manufactured material, and how this feeds into forming the properties of that material, and how this can then manifest itself in the final performance of a additive manufactured medical device. So additive manufacturing is a relatively novel and unique technology. It enables manufacturing of complex geometry parts, which are very difficult to achieve using conventional processes such as machining, forging, or casting. The way it works is we start with a three-dimensional model of our implant or our part, and that goes through a piece of software which slices that model into two-dimensional slices. Those are then sent to the 3D printer, which reconstructs those slices during the process. I'll focus mainly on powder bed fusion technology, since this is what most medical devices, metal medical devices, are manufactured with. And in this process, essentially a very thin layer of metal powder is distributed on a substrate known as a build plate, and a high power energy source such as a laser or an electron beam then traces that two-dimensional slice, that pattern that was extracted previously from the model, onto the build plate. And that process is repeated continuously until the three-dimensional part has been reconstructed. In my talk, I'll focus primarily on two key technologies: electron beam melting and selective laser melting. There are some differences in those technologies. I'll just briefly mention that electron beam melting, of course, uses an electron beam as its energy source, while selective laser melting uses a laser. E-beam generally has a larger powder particle size, which results in a faster build rate, but can reduce the surface quality somewhat, although with the caveat that this is highly machine and application dependent. Additionally, E-beam it's a hot chamber process, so the cooling rate which is experienced by the molten metal will be low relative to SLM, which relieves residual stresses and coarsens the microstructure. Additionally, E-beam is conducted in a vacuum, while SLM is generally conducted in an inert atmosphere, such as argon gas. I briefly want to touch upon the concept of a microstructure, as it's somewhat counterintuitive. If you think of a solid block of metal, you'll always think of it as a coherent structure. But if you look on the micro scale, you'll find that it's actually made up of a lot of different smaller substructures known as crystal grains. Now, crystal grains are essentially arrangements of the metal's atom, which are directionally aligned, preferentially in a certain direction. And there are many of these crystal grains, and they're separated by grain boundaries. And basically, the arrangement and orientation of these crystal grains is what's known as the microstructure. Additive manufactured microstructures are very, very much directionally aligned with the process within the build direction due to the flow of heat. And then if we compare a laser-based process microstructure to an electron beam-based microstructure, we see that the electron beam microstructure is coarser, so the grains are larger due to that hot chamber process, which also creates formation of secondary phases, such as the beta phase, whereas in laser-based processes, we generally have an as-built martensitic phase, which has implications for strength and ductility. Then I just want to discuss some of the defects which are found in additively manufactured parts. So there's a operating window which we should try to stay within. Here is just an outline of what this looks like for a laser-based process. So essentially, we don't want to have too high of a laser power and too fast of a scan speed. And we generally want to be in that optimal sweet spot range. Otherwise, we're going to get formation of various defects, such as keyhole defects, balling up, or lack of fusion. Now I want to briefly discuss how we could investigate our material in order to quantify or analyze defect content as well as the microstructure. So generally when we speak about doing this, we're talking about electron microscopy. And we can talk about scanning electron microscopy or transmission electron microscopy. SEM is more of a surface-driven technique, so it's quite useful for analyzing fracture surfaces and trying to identify certain defects which caused failure. Whereas transmission electron microscopy, it's essentially a nano imaging technique, which is very useful for looking deep inside the microstructure and trying to infer any property process relationships there. Another technique which is quite relevant on this topic is micro CT scanning. Essentially, we can scan a part and it will create a number of X-ray images, and it will reconstruct those X-ray images into a three-dimensional model. This is very useful because it can tell us exactly where defects are present, and we can do data analysis to extract key metrics about these defects. Specifically, we can identify the maximum critical defect within the material, and this can then feed into our quality inspection metrics for AM parts. It's particularly useful for validation of processes. I'll talk a bit more about the maximum critical defect size later when we talk about fatigue. Because we've got some tests that we can do to basically determine what is the maximum defect size which should be allowable within our part for our specific medical device application. And then I'd be remiss if I didn't touch upon more of a conventional technique for inspecting parts and identifying defects. This is actually a process we offer here at Croom as well for our customers. So this is a fluorescent penetrant dye inspection. Essentially, the dye is applied to a surface and it will highlight any surface cracks or surface defects from AM processes or casting processes, forging processes, and so on. And this is a conventional method of inspecting your parts. Since micro CT scanning can be quite time consuming, this is often a better solution for high volume production, although it doesn't really tell us anything about the internal defects in the parts. Now I will briefly discuss mechanical testing. I'll show a video of a tensile test and talk through it, and then how we can optimize strength and ductility primarily through changes in the microstructure. So here's a video of a tensile test. Basically, we use a standard specimen, which is agreed upon by standards. And we will mount it in a servo-hydraulic test rig, which will then pull the sample apart, applying a tensile load as it's measuring the applied force and extension. And we can then use that data, so that force and extension, to plot what's called a stress-strain curve. So a stress-strain curve is kind of like a characteristic fingerprint for a material's mechanical strength and ductility. And what it tells us is basically how any changes in our process have influenced the strength and ductility of the part. So if we look on the y-axis, we want to maximize the y-axis, so maximum strength, and on the x-axis, we want to maximize the x-axis for maximum ductility or formability as such. And we can see different microstructures will lead to different levels of strength and ductility. So for instance, this reference microstructure here, which is a wrought titanium 6-4 microstructure, it has very high ductility but relatively low strength. Whereas this, with the same chemical composition, I should mention, but just different heating history, we've got a very high strength but very low ductility due to the differences in the microstructure. So the data we get from the mechanical testing, tensile test, is useful because it feeds into the design process of implants. It will give the design engineer some constraints with regards to the geometries that they can create with additive manufacturing for their implants. But it's a highly idealized test. So in a real world scenario, we often have fluctuating stresses, complex loading scenarios, and we generally don't see implants failing due to static tensile loads. So it's important to consider metal fatigue. Metal fatigue, I'll talk through the different stages of metal fatigue and the different methods for testing. So there's 3 stages of metal fatigue. So the first stage is crack initiation. So a crack can form at a defect or a microstructural feature. It's a microscopic crack at first, but as you add a number of stress cycles, that crack can grow. And that's the second stage of fatigue, crack growth. So the crack can continue to grow until it reaches a critical size, where we then get fracture. So this is the power of fatigue. Essentially, a microscopic defect can potentially bring down an aircraft. So it's quite important to understand fatigue and understand how it impacts your process and products. It's estimated 90% of all mechanical failures are due to fatigue. And also the cost to the US annually has been estimated at 4% gross national product. So it's quite significant. So I want to touch upon the most important fatigue test, which is the Wohler or SN test. S stands for stress and N stands for number of cycles. The way that this test runs is we have a standard specimen and we apply a fatigue load, generally using a servo hydraulic test system, and we will decide on a maximum load, a maximum stress for that particular sample. We will test it under fatigue until it fails, and we will record the number of cycles which it survived. And we repeat that for a number of specimens to generate what's called an SN curve. So basically, we're testing different samples at different stress levels. We're generating an SN curve, and based on that, we can estimate the fatigue limit, which is a theoretical limit stress below which we're saying that there's no fatigue occurring. Now, it's of course prudent to add a safety factor to this, just to account for any statistical variation, since fatigue is quite a stochastic phenomenon. So the test I mentioned previously is very much crack initiation driven, but there is, of course, fatigue crack growth to consider as well. So there's a separate test for this. So I'm showing a video from MTS here. Essentially, there's a standard specimen type which can be used to simulate fatigue crack growth, and we can measure the growth of that crack as it moves through fatigue cycles. Now, I should say this test has been sped up somewhat, but this test could take anywhere from a couple of hours to a couple of days. And it generates a crack growth curve. And using that crack growth curve, we can infer the maximum critical defect size within a part before fatigue failure will occur, essentially. So this, again, feeds into our inspection, quality control, validation metrics, which we spoke about previously for CT scanning. So we could CT scan a implant essentially and verify that there's no defects of a critical size within that implant, and we can do this based on the fatigue crack growth test. And then finally, there is, of course, full-scale component testing. So the two previous tests mentioned are very good at characterizing the base materials property. However, in a real-world component, we've got many different materials interacting. We've got complex patient loading conditions, and then also we've got to consider the fact that the implant is inside the body, and there are some corrosive elements or wear mechanisms that can go on there. So generally, this will be conducted in a servo hydraulic test rig, usually in vivo with a special solution to simulate bodily fluids. And there's again a number of standards, ASTM and ISO, available to conduct that test. So now I want to discuss how do we maximize the performance of our base material with respect to fatigue, since this is our limiting design factor often. How do we maximize the base material's performance to get the most out of our implants? And I'll talk about the influential factors: machining, polishing, surface blasting, heat treatment, and hot isostatic pressing. So now we have a poll as well. So I would like to ask the audience, what do you think is the most influential factor or metric of additively manufactured materials that influences fatigue? And we've got three options. We've got internal defects, we've got microstructure, and we've got surface roughness. Okay, and I see that we've got quite a lot of responses now. 55% of you said surface roughness, 36% said internal defects, and 9% said microstructure. So you're actually paying a lot of attention in class then, because surface roughness is actually the key contributing factor, and I'll show some data now to prove this. So this is some data from Masao et al., which really nicely illustrates this point. So essentially, they produced material using laser powder bed fusion as well as electron beam powder bed fusion. And they were able to show quite clearly that if you do not polish your surface, it will have the most detrimental effect on fatigue. Whereas then if you polish your surface, the next most critical thing that you can do is apply hot isostatic pressing to remove internal defects. And I'm just showing an image here of how a fatigue crack can initiate at a rough surface. The reason that fatigue cracks like to initiate at rough surfaces is because these little crevices act as stress concentrators, and then also loads on surface stresses are a lot more amplified than internal stresses as well, especially when you've got a component that experiences some bending component in the loading. And here is what an internal defect looks like, which caused fatigue. So we're looking at a fracture surface here, and we've identified that this is a defect which caused that failure. Okay, so what can we do to kind of mitigate the effects of surface roughness? So of course we can machine our part, and we can do some polishing, whether that's hand polishing, mechanical polishing, electrochemical polishing. We do offer a range of machining and polishing techniques here at Croom Medical. Additionally, what we can do is surface blasting. So we can blast with a number of different media, and depending on the type of media used will have a greater effect on mitigating fatigue. So Essentially what this does is it creates a compressive layer on the surface, which will basically, fatigue requires a tensile component, so it will mitigate fatigue crack initiation on the surface. The next thing that we can do is a standard heat treatment. So I'm generalizing a little bit here. It is a bit more nuanced than this, but what we can say is that applying a heat treatment will increase the grain size, it'll decrease residual stresses, and it'll increase beta phase in titanium 6-4. And it will generally lead to an increase in the fatigue strength as well. And what's great is there's been a lot of studies done to basically tell us exactly what heat treatments we need to apply to achieve a certain grain size. So a lot of the base work has already been done and has been published in literature. And then finally, we can use hot isostatic pressing as kind of an additional fail-safe. This is really has been shown to work extremely well to remove internal defects. I'm showing my own research here. Where essentially, we printed material and we had some internal defects. We showed that a heat treatment itself didn't remove those defects, but then once we applied HIP, it really did remove all detectable porosity, which we evaluated using micro CT scanning. So now I would like to ask, how can Croom support your AM journey? So we can help you out with the development of implants, prototyping, DFAM, designed for additive manufacturing. We can help guide your 510K submission, also using our materials testing lab here on site. And then we can help you get your products into either serial production, and increase the capacity of your existing product lines. And we do have a lot of validated finishing and post-processing processes here at Croom Medical. So we think we can really support basically any AM project that you can give us. So now I'll pass back to Shane, who will wrap it all up here.
Great. Thank you so much, Bryan. That was excellent. Really informative and really interesting. We're now opening the floor to questions. So as I said, we have a Q&A box here. So if people want to put some questions in there, we have a few already, and we can get Bryan and myself to answer them. So I do see a question in there already for you, Bryan. So if you want to take a look, we have some interest from Andres about low temp, high pressure HIP. If you see that question. So it's, have you evaluated the low temperature, high pressure HIP as developed for TI-64 components? Is that something that you looked at within your research?
Yeah, thank you for the question. Personally, I haven't. Our HIP treatment was quite standard HIP treatment. So we didn't really veer outside of the generally used cycles. Yeah, fortunately not.
That's very good. I do see another interesting question as well about the temperature for, I presume, for annealing. So have you looked at temperatures above 900 C? So maybe that might be an interesting point for you to talk about the phase diagram for TI-64 alpha beta transition, and just to explain a little bit how that 900 C is quite important.
Yeah, so generally at around 925 C, we've got a phase transition into beta phase. If we are just targeting a stress relief, then we generally would prefer not to stay below that 925 C to avoid formation of excessive amounts of beta phase. But depending on what the goal is, we might want additional beta phase, we might want additional ductility. But yeah, for just a stress relieving heat treatment, you would generally prefer to stay below that.
And I see another part of Hannah's question there is about the interface between lattice structures and solid structures. So I think just on that one, obviously the heat treatment is very important. But going back to Brian's original point about how do we evaluate these structures, the type of test method we use for those is quite important. So where we're looking at solid and lattice hybrid structures, that interface is obviously not polished. It's a printed surface, but we can do tests such as shear testing, fatigue shear testing, and then tensile bond strength testing as well. So that's something we can do within our lab, and we've looked at previously. So I'm gonna see some more questions coming in here as well. So Brian, I see another question there for you in terms of evaluating fatigue performance at constant amplitude loading.
Yeah, so what I would say in that case for the SM test, you would always stay at constant amplitude. But when you go to more of the full-scale component test, then I guess you would want to get some data of how the patient actually behaves, and then use that data to feed into your servo-hydraulic test rate.
Okay, I see two more questions here as well. So there was just okay, in terms of the tensile bond strength testing. So I'll take that one. So in terms of tensile bond strength testing, this is something where we're trying to look at the bond of the lattice structure to the solid material. So what we're really trying to do here is pull in a tensile test the lattice structure from the solid, or have it survive a load above which we consider to be applicable or what necessary. So what we normally do is we can print the sample with a solid lattice, then solid, and have that loaded into our tensile tester to pull the structure apart. Or we could print solid lattice and then bond that top lattice, that exposed lattice structure, to a fixture with, say, an epoxy resin. Typically, it used to be FM1000, I think, but there's specific glues we can use for that. But we're really trying to look at a glue that's stronger than what we need the porous structure to be. It's a very important test for the bonding of lattice to solid. There was also another question regarding the additive manufacturing of porous structures, the typical deviation between as-built and as-modeled structures, and how can we minimize it? Well, I might take that one. It's quite an interesting question, because there's a number of different methods for us to make lattice structures, depending on the technology we're using. So if we look at the Renishaw system, one we have here, that uses point exposure method. So with that, we do not actually model a size for our lattice. The size of the lattice is controlled by the printing parameters. So we kind of have a known sort of input energy versus output size for the lattice. And we work with just the center point of the lattice as our design space, we'll call it. And then on some of our other systems, like the M2 system, for instance, we typically we don't really design the lattice structure if we're looking for thin beams. So if we're looking for, say, 100 microns to 2 or 250 microns, we don't model that. We might model it as a constant size. And then again, we change the print parameters. But if we go above, say, 300 microns above there, we might start to model the size. And typically the deviation can be quite minimal. We might be talking 20 microns or something like this above, but it starts to come down to your material, your print parameters. There's quite a lot of influencing factors in this. So it's a very important topic. I would see quite a few questions coming here, so I'm just going to scan through. So Brian, I'm not sure, there's a question there in relation to the contact points between lattices and solids in terms of stress concentration for fatigue. I'm not sure if this is something you've also looked at.
It's not actually something I looked at personally, but what I can say is for sure those are going to be critical regions, because you've got obviously that transitionary period where you've got sharp corners, which can act as stress concentrators. So I would say that interface region is definitely a region to critically look at and try to optimize your design as well as your process to mitigate fatigue crack initiation there.
Yes, I think it's a very important point. Surface roughness is going to be very important for us. So there's two other questions, I think. One for myself here, just in terms of the Renishaw system. This can use both modulated laser and continuous. So there's the option for us to use modulated laser where we wish, and continuous laser refurbish. And I do actually have some work previously with iForm that we've published on this as well, comparing modulated and continuous. So if that's something you're specifically interested in, I don't have your name here, but that's something you're interested in, you can feel free to contact us. I can send you the paper. There's a question there for you, Bryan, as well on conducting fatigue in as built or as machine state. So
yeah,
you want to take that one?
So I would say if you're just trying to investigate the base materials performance, I would always do it in as machine state or even actually as polished. So I think the ASTM standard actually calls for a surface roughness of less than 0.2 micrometers or A. So you would actually need to polish your sample if you want to adhere to that standard. Now, when it comes to more of like an upscale, full-scale component test, of course, you would keep it in that rough surface condition or whatever condition you're planning to implant your device in. So yeah, it really depends on which type of fatigue test you're talking about.
Okay, and I do see another one there from Franz Mohlmann. It seems more or less of a question than a comment, but it's a good one. So they've seen some differences between software in terms of stress concentrators related to filleting. So I think that's a very important point. It's kind of something we would do where if we're doing our design for additive manufacturing, is to actually look at the component, the potential for, as Bryan has mentioned, surface roughness that might influence fatigue, any sharp corners, any square edges, this type of thing. Obviously, they will act as concentrators, and if we're adding on porous structures, that interface too. So we'll pay quite a lot of attention to that. But it's something we'd work on during the design for additive manufacturing stage. I'm just checking here. There's a couple other so there's a couple of other questions here. I'm just having a look. Yeah, so Bryan, I'm not sure if you want to take that next question there in terms of ultrasonic cleaning. So some of that obviously we can't share in terms of the detergents and cleaning agents we use, but obviously ultrasonic cleaning is quite a good method for wet powder removal. So if you have any further comments on that one, Bryan.
Yeah, I would say specifically when you're talking about really fine lattice structures, you might find ultrasonic cleaning is not a fine enough process to remove those powders. So you might actually have to look into even megasonic cleaning.
Yes, if we're dealing with extremely small structures now, they would be smaller than what we typically expect for osteointegrative structure. So very good. So seems there's some more questions coming in here now. Feel free to add them in. So just one question I had for you, Bryan, as well, just in terms of your own research, was you mentioned CT scanning for defects, for detection of defects. So could you talk a little bit about the size of defects and the type of process that you've used for analyzing those defects as well?
Yeah. So defect sizes vary, of course, depending on the process. Generally, if you're talking about gas defects, gas pores, they would just be on the order of 2 to 20 microns, so relatively small. If you're talking about lack of fusion defects, they can actually get quite large, and obviously the larger they are, the more detrimental they are. And the critical thing about lack of fusion defects your shape, which leads to more stress concentration around that defect. There's a number of ways you can evaluate or a number of metrics you can apply to these defects, such as the sphericity. So generally, the more spherical, of course, they are, the less detrimental they will be. So if you've got a low sphericity, you know that defect's going to be quite critical. You can also use something called the projected area. Basically, it's the way that fatigue load works. It's not the full three-dimensional size of the defect that matters. Sometimes you can just look at it from one specific plane, and then basically do some metric of the defect on that specific plane, either equivalent diameter or surface area, something like that. So there's a number of ways you can evaluate the defects depending on your specific use case.
Excellent, very interesting. Yeah, I think it's a very interesting method and really interesting what you showed on that one as well. So, okay, so I think we're probably coming close on time here. So I'd like to thank everyone for joining us. As you can see, we have our contact information on here. So if you have any queries, if you're any follow-up questions, this will be available. The recording will be available as well afterwards. So again, I'd like to just thank my colleague, Dr. Bryan Naab, for joining us, and for yourselves for coming along today. And really look forward to hear from you if you have further questions, comments, or any inquiries. So thank you very much.